Hello everyone, I'm so glad you're here. Today in AP Calculus, what we're going to do is determine limits using algebraic techniques. So let's get started. For the lesson preview, you are asked to describe 4 reasons as to why a function may have a domain restriction. One of the obvious reasons is that you have a 0 in your denominator. It's also possible to have a negative under a square root. A third reason could be that you have a negative in the argument of a logarithmic function. A fourth reason may not be quite as obvious until you think more carefully. You might have some sort of physical restriction. For example, if you have a board that is 10 feet long and you're told to cut pieces of board that are 12 feet, that wouldn't work. Question B, you're asked to describe 3 reasons why a limit might fail to exist. From the notes that you previously took, you know that the left and right sides have to be approaching the same value. So if they're approaching different values, your limit would fail to exist. The function might oscillate, which could also be a problem. And it's also possible that the left or right side of the domain does not exist for the function you're evaluating. So for question C, you are asked about the limit. Now the limit is the y value that the function approaches. Is it necessary for the x value to be in the domain of a function to have the limit exist? And I'm hoping that you came up with the x value does not have to be in the domain. Because remember, your limit is approaching that x value. You don't actually have to touch it. After completing your lesson preview, it's time to really get started with our notes. So let's take a look at our first example. So today we're going to determine limits using algebraic techniques. But in order for that to work, I want to make certain that the connections from the graphs to our functions are working properly. So let's look at the graph first. The limit as x approaches 1. Now, it doesn't say which side, so we're going to have to approach from both the left side and the right side. Now, as you can see, the y value that we are approaching is 2. So according to the graph, the limit as x approaches 1 from both sides of f of x is 2. Next, we're going to explore to see what would happen if we were just to substitute the value of 1 in for f of x. If we do that, we get 3 times 1 squared plus 1 minus 2, which once again is 2. So substitution seems to work for this particular problem. If we look at question B, the limit as x goes to 10 is not on the graph. It's not highly convenient. So will substitution work again? Let's give it a try. If we take 3 times the quantity, 10 squared plus 10 minus 2. If we do that substitution, there are no jumps in the graph, there are no holes in the graph. We just fill it in, substitute, we get 308 as the value. So substitution will work when we have a nice polynomial function such as f of x. Now let's look at question C. For question C, we're approaching -3 from the left side. Now, as I approach -3 from the left side, should it make any difference if I'm looking at the right or the left side if we have that nice polynomial function? The answer to that is no. So we're going to, once again, substitute -3 in for f of x to determine our limit. So once we do that, we will end up with a 22 as our answer. So the limit as x goes to -infinity is asking us to look at the left tail of the graph. Now the left tail of the graph we can see goes towards positive infinity. So once again, looking at the graph can give us an answer. However, if the graph's not there, let's once again try substitution. 3 times -infinity squared, and that's very strange, minus infinity minus 2. Now, think abstractly. -infinity squared is actually much bigger than -infinity. These two terms at the end are considered lower order terms because x to the first power is not as powerful as x squared, and of course the constant 2 or -2 is not as powerful either. So what we're going to do when we think about going to -infinity for this nice polynomial function is we're going to drop our lower order terms and only consider what's going on with the parabolic function 3x squared. When you substitute the negative in, the negative becomes a positive. It's squared. Once it's squared and multiplied by 3, it gives us positive infinity. So we don't need the graph in order to figure out limits for our polynomial functions. Now, when we look at example 2, different things are going to happen. We have x squared minus 9 over x minus 3. So we want to always remember to use our correct notation. And as we think about the limit is x goes to the 2. Well, we're just going to try substitution. The limit as x approaches 2 for this function is going to be 2 squared minus 9 over 2 minus 3, or as you know, this is going to be a 5. Now, the correct notation. Once you do the substitution, you do not need to write the limit notation again. However, you must write the notation until you actually do the substitution. For example, B, I have a limit as x goes to 3 for x squared minus 9 over x minus 3. When I do my substitution, oh no, you see my problem here, I hope, you get a 9 minus 9 over 3 minus 3, which is 0 over 0. So that's a problem. We're going to have to do a little bit of factoring in order to determine this limit. So we take the limit as x goes to 3, write the factors x minus 3 times x plus 3 divided by your x minus 3, and look at that. The factors x minus 3 do cancel out, which then allows us to substitute the 3 in. Now remember what I said. Once you substitute, you do not have to write your limit notation anymore. So 3 plus 3 is going to be 6. Now let's focus on question C. The limit as x goes to negative infinity for h of x. That, when we think about it, is the limit as your x goes to negative infinity, so that's your left tail, x squared minus 9 over x minus 3. All right, so once again, let's think about what's actually happening with this function. The x squared minus 9 is a quadratic. The x minus 3 is linear. The quadratic has a lower order term of negative 9. If I cancel out my negative 9, the x squared is going to be the more powerful piece of this function. In your denominator, you have x minus 3. So the negative 3 of the line is not as relevant as your x. So essentially, we drop our lower order terms and we end up with the limit as x goes to negative infinity, x squared over x. Now, this is not algebraically legal without the limit notation, and that's what makes the limit notation incredibly powerful. So now x squared over x can reduce to x. When you substitute negative infinity, you get negative infinity as your answer. I also told you that, remember, we were going to think about this problem in terms of graphs. When you have h of x, it's the line x plus 3, which is heading upward. Now, the line of x plus 3 has a hole in it at x equals 3. So it's just a line with a hole, and as you look at your left tail, it is heading downward. So algebraically, drop your lower order terms whenever you have a rational expression, and then you'll be able to find your limit as you go to plus or minus infinity. So I want you to think about these two problems. The first one is, so as you think about these two examples, the first one is an example of a polynomial, and substitution works very nicely. The second one is a rational problem, and the rational expressions, you can think about your limits. Or as you think about your limits, you should look for factoring, removable discontinuities. Now, our third example is actually the one that throws people off. So the graph of our third example becomes really important. We have g of x equals 5, so we're going to determine the following limits. The limit as x approaches -1 for 5. So think about for a minute what your graph looks like. G of x equals 5 is a horizontal problem up 1, 2, 3, 4, 5 steps. Now, as you approach -1, you're approaching from both sides because it doesn't say plus or minus. The answer is 5. So the limit of a horizontal line is 5. It doesn't matter what you're approaching. For question B, I'm approaching x is 10. Well, the answer is 5. For question C, I'm approaching -2 from the left, and the answer is 5. And for question C, as you approach negative infinity, D, you are going to 5 again. So the range of g of x is 5, and we're going to classify this as an example of a constant. So a limit problem with a removable discontinuity occurs when you try to substitute. You always should try to substitute first, and you get an indeterminate form. There's a new definition for you of 0 over 0. Now don't write 0 over 0, but if you get this indeterminate form, there are many algebraic techniques that you could use to try to figure out how to remove the discontinuity. You might try factoring. You might try long division. You could multiply by a conjugate. You could use a trig identity, or you might find a least common denominator. So, for example 4, I'm looking at my problem. If I substitute the 0 in, look at this, I get square root of 16 minus 4. Well, that of course is 0. And divide by 0. So substitution in here fails. I have an indeterminate form. I should not write 0 over 0, but what I should do is use one of my algebraic techniques in order to rewrite the problem. Keep your notation, the limit as x approaches 0. And now for this one, notice I have a square root. I'm going to multiply by a conjugate, because I know if I multiply by the conjugate of this square root, then I will be able to unravel that square root. So I'm going to multiply by the square root of 16, x plus 16 plus 4, and what happens when you do that? Their numerator becomes a lovely x plus 16 minus 16. Now that happens because you have a difference of squares that you're multiplying. That's what conjugates are for. Now your denominator, we have x times the square root of x plus 16 plus 4. I suggest you not actually multiply that out. It never turns out pretty. Just leave it alone. So do a little bit more algebra. Keep your limit notation. The notation becomes incredibly important here. Then we'll have x over the x. Oh, there's the square root of x plus 16 plus 4. And look at that. Your x is now in the numerator and the denominator. They will cancel out. Keep your limit notation one more time. The limit as x goes to 0 for 1 over the square root of x plus 16 plus 4. Now, we're at a point where we try substitution again. And when you try substitution again, you get 1 over the square root of 16 plus 4, which is 1 over 4 plus 4, or 1 over 8. So the limit of our original problem is going to be 1 over 8. Notice though, we always try substitution first and use the correct notation as you work through each problem. All right, now for the next one. It looks like we've got some trig going on here. And the sine of 2 theta, when I substitute pi in, the sine of 2 pi is going to be 0. And the sine of theta, when I put a 0 pi in again, is, 0. Not allowed to write that, remember that. So this is an indeterminate form. I'm going to have to use, a trig identity. So I've got the limit as theta goes to pi, and the trig identity we're going to use is the sine of 2 theta equals 2 sine theta cosine theta. And you thought those trig identities would never come into work. Well, here we go. Now, as you do that, notice your sine of thetas conveniently cancel out. Keep your limit notation. We have the limit as theta goes to pi and 2 cosine theta. Now from here, we're going to try substitution again. And when you try your substitution, you get 2 times the cosine of pi. And today the cosine of pi will be -1. So 2 times -1 is -2. Notice when I did my substitution, I stopped writing the limit notation. Take a look here. It says each time a trig identity is used, you are responsible for knowing it for the rest of the course. No excuses. So make a running list to keep track. Here's your first one. You're to know that the sine of 2 theta equals 2 sine theta cosine theta. Put that in the list of things that you know. All right, here we go. So for example 6, we have the limit as your delta x goes to 0. Given this function, oh, look at that, a complex fraction. My least favorite thing to deal with is a complex fraction. So what we're going to do is try substitution first. When you substitute your 0 in, you get 2 over x minus 2 over x divided by 0, and you know that's 0 over 0, which we don't write, so erase it. You get a 0 over 0 form, and we're going to have to do some algebra. So what algebra should we do? Let's think about it. The algebra that's going to occur, we're going to find common denominators. This becomes the limit as your delta x goes to 0. So when I find a common denominator, I multiply 2 times x minus 2 times x plus delta x. My new denominator is going to be x plus delta x times x, and you know what? Delta x will always end up in the denominator. You can check it out if you like, but we've just taken our complex fraction and rewritten it into something more manageable. Notice delta x goes to 0 is still being written. The limit is delta x goes to 0. We do more algebra. You have your 2x minus 2 delta x. Don't forget to distribute that negative. And once again, do not multiply the denominator. It is not going to be useful in the long run to multiply it out. You can see that your 2x and -2x do cancel out. That's highly convenient. The limit as your delta x goes to 0 is then -2 delta x over that denominator, which I know you are enjoying writing each time. But as we look at it, notice the numerator has a delta x, which is a single variable, and your denominator has the same delta x. They conveniently cancel out, and we're left with the limit as your delta x goes to 0, -2 over our x plus delta x, x. Now, don't be confused here. Your delta x is going to 0. Delta x goes to 0. So we did our substitution, and we end up with -2 over x times x, which is x squared. Whew, there you have it. You just found your first derivative. Yes, through this limit process, you have found your first derivative, which might not have meaning to you right now, but it will later on. All right, so for example 7, you have your 3x cubed minus 5x squared minus 3x plus 2. So what we want to do is, I don't know, let's try substitution. Always try substitution first. And unfortunately, guess what's going to happen? When you put your 2 in, you're going to get 0. When you put your 2 in your denominator, you get 0. Oh no. So 0 over 0 means that there's a factor in here of x minus 2 somewhere. So you're going to have to do one of two things: synthetic division or polynomial long division to figure out what the other factors are. Now you get to choose your method. If you like synthetic, please use that. I will always use polynomial long division because I think it's a little bit easier, but everyone does what they need to do at this point in their algebra career. So I know that 3x squared times x is 3x cubed minus our 6x squared. Then I will subtract, which changes all my signs to give me positive x squared minus 3x. I know then that's a plus x, multiply again, x squared minus 2x, change all of my signs again, which gives me negative x plus 2, which tells me my third term is -1. So when I rewrite my problem, keeping my limit notation, I have x goes to 2, the quantity x minus 2 times that quadratic 3x squared plus x minus 1 all over x minus 2. Very conveniently, the x minus 2's do cancel out as expected. And keeping my notation consistent, limit as x goes to 2 again, 3x squared plus x minus 1. I'm ready to substitute my 2 in. I get 3 times 2 squared plus 2 minus 1, which is going to be 13. Now notice, once again, once I did the substitution, I did not write the limit notation. And it's time for you to practice. Notice the lesson practice is short. It says only 10 minutes. So really, I want you to stop after 10 minutes. Do not do it all. If you finish early, that's great. If you don't finish it, that's really okay too. So practice with the substitution, and notice there are a few questions in here where the substitution might not work out so easily. So no more than 10 minutes for the next couple screens. So stop the video, give these a try. I will provide you with some answers once you restart. So for numbers 11 and 12, you needed to multiply by the conjugate. The toughest part about question 13 was multiplying 4 times the quantity x plus delta x squared. So take your time doing that one. The answers have been provided. Question number 14 was a factoring problem, so make certain you are awesome at factoring. 15, you either had to factor or use long division, whichever way you prefer to do 15. 16, you had to find the least common denominator in order to solve it. And for question 17, you're going to have to multiply the quantity x plus delta x cubed to eventually come up with your answer. So I want to talk about that quantity, x plus delta x cubed. This type of problem is very easy to multiply out if you are using Pascal's triangle. So the way Pascal's triangle works, you have your coefficients. You start with 1 at the top of the triangle, then 1, 1, 1. You add the 1 and 1, you get 2, and we go forward, 1, 3, 3, 1. So for polynomial multiplication, if we use Pascal's triangle, that tells us the coefficients of each one of our terms. So as we multiply out x plus delta x squared, the first term is 1x cubed. So we take the first term and we're going to cube it. Then we're going to take the value of the number, which is a 3 in this problem. So we want the 3, 3, and then the 1. So we're going to write our 3. The x, which was your first term, is squared, and then the next term is just delta x. The exponents should always add up to 3. Then we're going to have plus 3 x to the first power, and then we'll have delta x squared, and then our last term is plus 1 delta x cubed. So you can use Pascal's triangle in order to multiply out any of your binomials, squared, cubed to the fourth power, all sorts of good things there. Okay, so the properties of limits explored so far. When we have a constant, no matter what value we approach, as x approaches that value, your answer is the constant. Substitution can occur for lots of polynomial expressions and for exponential expressions. So if we substitute in the value of c for c to the n, we get c to the n. The properties of limits that we should also consider. Addition is permitted, subtraction is permitted. You can multiply. Division, it works well, and also raising powers to exponents can be used. They're very powerful. A limit will only exist at the value L if and only if the limit from the left side of A equals the limit from the right side of A. And to wrap it all up, common types of behavior that are associated with the non-existence of a limit. If f of x approaches different numbers, the limit does not exist. If f is increasing or decreasing without bound, those are called plus and minus infinity. If f of x is oscillating between two fixed values or multiple fixed values as you approach c, then that limit does not exist. All right, you guys have been doing a great job. I'm very pleased with your work. You should be proud of yourself, and I will see you during the next lesson. So today's lesson follow-up is on page 67, and I just wanted to send you a reminder that you should not be working for more than 60 minutes. Make certain that you pace yourself and enjoy your practice.